All right, I'd like to start today's lesson, if there are no more questions about the things you see before you, with us focusing on C from today's warm-up and conducting a little bit of an experiment. I'd like you to rework the problem for C with, instead of 20, a 50 here. Could you do that for me, please? It's not a problem. You have a formula that makes this as easy with 20 as it is for 50 in the top there. So that'll just become a 51, right? All right, so everything's fine. Stop complaining. Okay. When you come up with an answer, turn to your neighbor and give them a conjecture that you have about this situation, what you think is happening and why, maybe even some explanation for why it's happening. Tell them what you're seeing. At least not the same thing. When you are done, do it again with 100. And again, form a conjecture about this situation.
Or 500, or 7.5 billion, approaching the same number.
Conjecture do you have about this?
My conjecture is that 8 is too much for my time.
Just the number 8.
Those are very good. Having the conjecture form.
42.
Maybe you want to make a broader conjecture, not just about this problem, which I hear a bunch of people coming to some conclusion on this interesting question, or at least this line of questioning I'm bringing to you. But maybe you have a general result that you want to make some conjectures about too. Like, why is this happening on a larger scale? And if you're the kind of person that's interested in the answer to that question, then boy, do I have a lesson for you. Okay. We would like to think about this situation where we are adding up, or whether this even makes sense, to add up an infinite number of things. Which is, I think, the conjecture you're making about part C on the warm-up. What is the conjecture? Someone say it. Now give me a well-formed sentence that includes the number 8 in it. All right, let's do it one at a time. Camera first.
As the amount of terms continue to rise, the sum will converge on B.
Oh, very technically said. Do you want to say it your way? Someone else? Let's give a sentence still.
It's really close to that.
It gets really close to 8. Okay. As what happens? What gets close?
Numbers get higher.
Yeah, as the upper limit gets higher, or the number, whatever. Yeah, as the. Ian, say your way. Go ahead.
I was actually going to make a conjecture, I think. For whenever you have the largest possible fraction of the numerator over denominator without ever reaching 1, with both numerator and denominator being whole numbers, and you have a constant in front of that you're multiplying it by.
That's how conservative you are. Like, only in this 15 years.
From what I've found. So but it seems to approach the limit of the denominator times the constant. I've tested it with 4/5.
Okay, so you tried another series. That's cool.
So I'm going to do it with more numbers.
So at the very least, let's take away from what Ian's just said that he thinks that, and you can easily check with another series that you come up with, that it does seem like something more broad than just this problem is going on. So I think that's worth mentioning, whether we want to think about maybe how broad. But he has brought that to our attention. Why don't we save it for now, Ian? Sorry, I know you're excited. Okay. You do have to write down, hold on to your hat. Okay, that's required. I'll give you a minute to draw the pictures.
Well, that's something new.
Okay. All right, let's first examine this symbol and even think together. What would this even? How could this even mean something? To add up an infinite number of things, regardless of what might be here. Remember, the AK that is a stand-in for some explicit rule, whatever it might be. It might be 2 times 3/4 to the K, like on the warm-up or something, whatever rule it might be. But in general, how can someone be asking us for this problem with an infinity in the upper limit of the sum? And I think you've already begun to see how that might be something we can make sense of, looking at part C of the warm-up. We use this definition to unpack what this means. And it really does come to what you said on the warm-up. Didn't you add up the first 21 terms, the first 51 terms, the first 101 terms? And in each case, those were not the infinite sum, were they? Those were what you might call a partial sum. And the thing you observe is that the partial sum, that is, each of the finite sums, if you were to write down your results, here's what I got for the sum of the first 21 terms, 7.98. And you were to write down, here's what I got for the sum of the first 51 terms, 7.99, not whatever it was. And you were to write that down, then those partial sums that you're computing would converge on a number. And that's the number that we say, that we assign as the value of this infinite sum. But here it is more technically in a yellow box, okay? So here's our trick. This equality here is the trick. We say for any finite sum, this is well defined. I'm covering up the limit for now, but you understand that no matter what crazy series we might have, if you give me a finite sum, that's something that always, regardless of the series, always makes sense. Now the question is, does it still make sense if we let that upper bound approach infinity? That's an important question. But this is kind of how we handle the situation. And this maybe is a little weird for us to assign it the value 8 in the warm-up. But that is in fact what we'll say, and we'll see that that's actually not that weird in a minute. Yeah, Franklin. Maybe, I don't know. Yeah, Cameron.
When you're taking partial sums, do they all have to start with a certain bottom number? Could you do K1 to N of 50 and then K of 51 or does the bottom number change as?
No, the bottom number shouldn't change in this case. We want to be adding up the first term, the first 2 terms, write it down. Add up the first 3 terms, write it down. Add up the first 4 terms, write it down. And if that sum, that running total, very similar, I think, in feel to how we can calculate cumulative frequencies in the stat unit, right? This number represents the current term, along with the sum of every other term below it, right? Yeah, Annabelle.
I don't understand how it could converge if you add up the first 20 terms, because if there's an infinite number of terms, then wouldn't it just keep getting bigger and bigger?
Yeah, doesn't that kind of just bake your noodle? Right, that's hard to think about, but that's true, right? So, would you agree that this is the result we have from the warm-up? Because this is how we're going to write it. Don't you agree that it seems like there's a sense in which it does get bigger and bigger? That's true. But does it ever, are you suggesting that it will get to 9? If we go far enough? Okay, well, we haven't unpacked why this would be necessarily. That's a good point. So maybe she's casting doubt on the conjecture that you all made in part C of the warm-up. She says that maybe you just haven't gone far enough. Infinity, she says, is a long way away. Okay, so what are you doing making claims about what happens if we add up? You only add up the first 100 terms. In infinity's world, that's nothing, she says. Maybe it gets to 9 eventually. She has a valid concern, doesn't Annabelle? But this is, for you, those who had a conjecture in part C of the warm-up, I think this was your conjecture, said in the notation of this slide, yes? That the infinite sum equals 8, yeah. Yeah, we haven't said anything about others. This is not only for geometric. This happens to be geometric, though, you're right. Yeah, and we are going to make a special note about geometric today. That's going to be our focus. But in general, this is a bigger discussion. And we're going to discuss it in the context of other series as well, besides geometric. Yeah. So this applies to everything, is what we're saying right now. So, yeah, do you have a question? It's a little unsettling still.
Sorry, can you like say the long equation in normal words again?
Yeah, sure. It said kind of in normal words up here, and then it says more precisely we say. But I'll read it out loud and see if this doesn't say the same thing here. If the sum, as k goes from 1 to infinity of a sub k, of some, right, so this here is the infinite sum, which is just equal to this, we're saying. If this equals some number, that is, if you take the limit, this is what it says up here, the limit of the partial sums. What's this? For any given n, that's a finite sum, isn't it? So we're saying, by this we really just mean this. And by this we mean the limit of the partial sums, which is exactly the experience you felt in the warm-up as you added up this value for n that were closer and closer to infinity. If that approaches a number, say 8, and we say that that s value that it approaches is the sum of the series. And we do use the symbol equals to describe that situation. Yeah. And if it doesn't, if you add up the first 10 terms, then you add up the first 20 terms, and it doesn't seem to be converging to something, now that seems like a pretty empirical way to say it. Just like see whether it converges or not. But we have more technical ways to talking about it in a minute. If that doesn't seem to approach a number, like what's happening in part C of the warm-up, then we would say, like it says in the second part of this, that the series is divergent. The series, now we're talking about the series diverging or converging. To be clear, so the series is going to 8. That is the sum of the terms. What does the sequence, though, approach? That is the terms themselves. What do they approach? No? As k grows large, what do the actual terms, what are the things that we are adding up getting close to? No? That is, I'm just asking, what's this? What's the limit as k goes to infinity?
0.
Of 2 times 3/4 to the k.
0.
That is the terms themselves. The sum is going to 8, right? If you add up all the infinite number of terms, you get 8. But each term, though, as you go progressively further in the list, is approaching what number? Yeah, that's just like the horizontal asymptote of the function of the terms, right? Do you agree? It's exponential or geometric, whatever way you want to say it. Or it's like exponential decay, right? So we want to make sure we really have both of these things very clear in our heads. The terms themselves are getting ever closer to 0. When we add them all up, we get something that's getting ever closer to 8 as we add more terms, right? We'll say it again and again throughout the rest of this discussion. Well, let's start at least by talking about the two kinds of series that we studied a lot, and then eventually we'll move into other kinds of series too. But certainly it's worth saying right in the onset that arithmetic series don't converge, right? It doesn't really, you should almost go without saying that that's true. If you keep adding numbers to the series, it will get bigger, yeah. And those numbers are always the same number.
Why is it you can't pair off numbers in an infinite sequence, like the textbook gives you 1 minus 1 plus 1 minus 1 example?
Yeah,
Why can't you pair off numbers in that?
Yeah, so the associative law for a divergent series, the associative law, so the associative law that you know and love, that like A plus B plus C
Yeah.
is equal to A plus B plus C, works as one of the field axioms, and it's like one of the basic things you know and love.
Mm-hmm.
But it's an axiom that works for 3 symbols, right? And we can extend it to 4 symbols, right? You could prove it for A plus B plus C plus D. Using this law, you could use it to prove the case where you have 4 letters too. But the associative law, it's not axiomatic that the associative law holds for an infinite string of things. Right? So, like if you do 1 minus 1 plus 1 minus 1, which is what you were suggesting,
Yeah.
you say, well, I think that that should be equal to 0 is what you're claiming, right? But what if you reassociate them this way,
Mm-hmm. You get 1.
right?
Oh, and it gets better.
So which is it? And the answer is it's neither. It diverges, right?
It gets better.
Let's actually not talk about this yet, Dean. I don't think they're spiritually prepared for this yet.
But
Okay?
what about if you subtract 1 from it?
I don't want to talk about it yet, Dean. I understand where you're going with this, and we'll talk later, okay?
I'm sorry,
Yeah.
I've been reading
So
that up
you're
too
just
long.
saying divergent if it's like that, right? Like,
Yeah, all I'm saying is all bets are off if you have a diverging series. So you can't, the associative law doesn't Anyway, there's some interesting results with infinite series that we don't want to talk about right this second. Okay. All right. Let's turn our attention though to the one that was in the warm up today. And some of you have already noticed that was a special kind of series. What kind of series was that we were talking about in part C? That's geometric, right? So if we have a rule, and we do, for the sum of a geometric series, then maybe we can generalize the result from part C. The sum of a geometric series is what? A1 times 1 minus r to the n over 1 minus r. Great. Now, do you have any hunches yet about when such a geometric series will converge? The one the warm-up did.
When R is a fraction?
Yeah, or more precisely. What'd you say?
When R is less than 1.
Yeah, when r is less than 1, because obviously a fraction like 4/3 is not what you, I know what you mean. We all know what you mean. And we do require that r be less than 1 for this conversation to happen, if we think that it's going to converge. Okay, so now let's consider this sum as n grows large. All right, so what happens to this expression? Now, the only thing that's happening is n is growing large. All the other things are sticking with their current value. A1 and r are still the same. What happens when n gets large? And we have this provision. Yeah, what happens to this r to the n together? As imagine, r is like 1/2. And n is like 1,000,000. So yeah, this whole thing, r to the n, goes to 0, doesn't it? Leaving what? Yeah, just 1 so in general, what's the rule for the sum of a geometric series? If r is in absolute value less than 1. You're looking at it, yeah, a1 over 1 minus r. Okay. So now also try that on the warm-up problem. Does that work? What was the first term? Part C was 2, right? Over 1 minus 3/4 was the common ratio. What does that give someone? Does it work? You alright, Franklin? You have a comment you want to share with the class?
Yeah, I ate ramen for breakfast.
That's a beautiful thought.
That was a beautiful thought.
I poured water in it, so I was like, oh no, I'm gonna get bloated.
Franklin,
Yeah, okay.
bring it back on message here, friend. Okay, could you give me the answer to this question?
I ate ramen for breakfast. That was a big point of mine.
Oh, it hurts. Okay. Yeah. All right. I mean, we get you. Okay. Yeah. Does it work out to be the same as what we said it would? It seems like this seems to be working here, and I think we're making the claim that for any geometric series with this property, then we can have this result, and we can sum the infinite series. Again, that's still a little unsettling, I think, for some people in this room, maybe everyone in this room. Anyone else want to say anything about that before we move on? Let's try next considering this like partial sum definition of convergence. So let's find the first 5 partial sums. This is why I hesitated a little bit when you asked, and someone was asking, do we need to know Franklin's definition? Do we need to know that definition? In some sense, yeah, I do want you to understand this idea of the partial sums converging. Yes, absolutely. So let's actually watch them converge in front of our eyes if we think they converge. So I'll give you a hint. S1 is 0.3. S2 is, you see how this is like cumulative frequency? It's just kind of a running total, right? S2 is 0.33. That's the sum of the first 2 terms. You see where this is going? Okay. S3 is, this is nice on this one, right? S4. And I want you to do this on all 3 of these. And if you think it converges, say so and say what it converges to. So does this first series, let's answer for this first one, does this first series converge? And to what? Yeah, it looks like it's converging to a third. Now, I want to pause here and just realize with you that I think some of you have been really hesitant about the whole equals business. On the last result, you're thinking like, really? In fact, as you described the part C warm-up, as I was saying, like, let's throw an infinity in there. You wanted to use the word like, it approaches 8, or it converges to 8, or it gets close, whatever we want to say. It gets close to 8. But I think a lot of you are hesitant to say like, it is 8. The infinite series is 8. And yet, you have no problem saying that this infinite series equals a third, right? Haven't you always, you're not like, well, 0.3 repeating is like, kind of like 1/3, or it approaches 1/3. You don't hedge at all, do you? You're like, 0.3 repeating is 1/3. Let's move on, right? Well, hold on. In fact, that's almost so flammable that we shouldn't give it to elementary students, right? Like, really, we shouldn't ever talk about 0.3 repeating, even though I think that your first exposure might have been in elementary or middle school or something like that, until you've had a discussion of infinite series, because 0.3 repeating is an infinite series. You don't give infinite play toys to young children, but that is in fact something that you've always lived with. You're not like, oh, it's about a third. You're like, it is a third. So I want you to have the same, if you feel confidence there, and maybe I've shattered your confidence in that result, so that's fine. But if you feel confident in this, then you have to feel confident in the previous result. That equals 8, the infinite sum for part C of the warm-up. All right, let's compute the first 5 partial sums on this, and I'll entertain one question from you, Ian. Go ahead. Go ahead and work these out.
If you multiply that by 2, you get 0.9 repeat, which would be equal to 3/3 and be equal to 1.
Then you reject that result?
Not necessarily.
I think everything you said is great. All right. We'll bring that problem back to your attention soon enough. But all right, so let's compute the partial sums for these. Go ahead and do it. No, Ian. Calm down. I know it's exciting. Maybe you have an opinion then about this one, Ian. This is the same problem, isn't it?
Yeah.
Okay, so for this part B, Cassie, if you're ready, why don't you give us the first, where are you? The first 5 here.
5, 15, 30, 50, and 75.
Agreed?
Yes. And it does not.
Right, it's clear that those partial sums, this is exactly what we're talking about. Do the partial sums converge is the question on the table, right? And that is to say, does this sequence, 5, 15, 30, 50, 75, does that get closer to a number? Someone might be like, well, maybe someone says, it's not obvious to me, I don't know. I think the sum is 500. Right? Well then, if you claim that the sum is some number, say 500, then it would be very easy to show that that's incorrect by just finding a place after which this sum exceeds 500, right? And then that person might be like, well, oh, gosh, I meant 1,000. Well, then we can maybe prove, so if you really wanted to prove that this diverges, that might be how you would do it, is that for any upper bound that someone places on this sum, then you can always, regardless of what bound they give, find a place after which it gets bigger than that. Right. I mean, in some sense, you could say that this is an infinite, that the answer is infinity on this one, right? It diverges in that way. It goes off crazy to infinity. That would be a fine way to describe this too, yeah? I think that's worth mentioning because it's different down here, okay? What are the partial sums here? Leo, if you can handle it, go ahead. It's pretty extreme. Good. Very good. Mm. You're doing so well.
Okay.
Good. Very good. Huh?
No, you're wrong.
What's that 5? Good. Yeah. All right. Good. Yeah. So yeah, this is just us adding up the first, and then the first two, and then the first three terms, etc. And then the question is, does this sequence 3, 0, 3, 0, 3 get arbitrarily close to a single value? Does it have a horizontal asymptote, or however you want to say it? This sequence diverges, and so the sequence of partial sums diverges, and so this series diverges, no matter what the end says. Okay? Don't let him cloud your mind. Now on this one, you wouldn't say, though, I want to highlight these diverge in kind of different ways, don't they? You wouldn't say this goes off to infinity, though, would you? Because it doesn't. In fact, this is always bounded. One other thing I want to note again on this slide is, on A, the sum of this infinite series here, this infinite series is 1/3. What do the terms go to themselves? The actual terms. The terms themselves are getting closer to 0. So again, let's make sure we always have clear in our minds both things. What are the terms going to? 0. And what does the sum go to? 1/3. We have to make that crystal clear at every move in this game. Okay. Now, what kind of series, by the way, is this? It's a geometric one again. What's the first term? 3/10. What's the common ratio? 1/10. So does our formula work? Sure. You get 1/3? Good, math works. Okay, let's move on. All right, you are the paper master. You love paper. And you have two friends who love paper, and you want to give them some paper. They ask for paper. You have one piece of paper in your life, and you're going to give them each exactly 1/3. So if you'd like to follow along, feel free to follow along at home. Yeah. You can do it. Yeah, sure. And it'll breaks my heart when you ask them it's going to be on the test.
Not an answer.
Yeah, the life test. Yeah, we'll be. Okay.
Thanks for
All right, so the paper monster is giving. I have pictures here too.
Paper monster.
The paper master, excuse me.
Oh God, the paper monster's come for us.
The paper master is dividing in the following way. The paper master, you, the paper master, retain 1/3, and you give 1/3 to each of your friends. Now, here's the thing. They really, really liked your gift, and they're really anxious for more. So you're gonna, you having only 1/3 of a paper left, as generous as you are, you decide to give them again 1/3 each of the paper you have. So Camber's demonstrating here. I have pictures here. So of the strip you have, you cut it into 33 pieces, and now they each have 1/3 of that, which is actually, with respect to the original piece, how much? That's 1/9. So they now have 1/3 of the original piece. They also have now 1/9 more of the original piece. And how much do you have?
1/9.
You have right now in your possession 1/9 of the original piece of paper. They love your paper gifts.
Isn't that like a problem where it's like if you can fold a piece of paper in half 20 times?
Yeah, there's no folding involved here though, but
Well, no, but like it's like.
you're right. There's a geometric sequence afoot in that problem that you're speaking of. Yeah. They love your gift, so we do it again. How much do I have now? 1/27th of the original piece of paper, and they each have 1/27th more than they had in the previous iteration. They love this. They love your gifts. You are the most beneficent paper master that has ever come to pass. Your paper just keeps shrinking, but you're just still generous as can be. I guess we should ask at this point, how much paper will I have if this continues? I will have, me, personally, if I'm the paper master. Yeah, an amount that is vanishing, right? And how much will they have, each person individually? Well, it's a bounded amount, isn't it? It's not an infinite, it's not like they'll ever have more than what? Yeah, each of them eventually, if we continue this process, will have approximately half the paper that we started, right? In each of their piles. Oh, we should do it again. Yeah, there we go.
I can't go further.
You can't go any further? Oh, well, you're just not trying. Okay.
You're right.
Get some scissors.
I can do
Yeah,
more.
you want some scissors?
I can do better.
If this continues, how much paper will you have? You told me the answer was 0. Yeah, how much will each of your friends have? They'll each have half, which makes sense, because in the end, in a limiting condition, they each have half the paper. You have none. It still adds up. Everything, conservation of matter, everything's fine.
Should a sister shouldn't happen.
What would happen if you split the atom, but then neither of you would have any paper?
How much did you give them initially?
One.
1/3? So what we're saying is your pile, you can think of, if you're a recipient of the paper, you can think about it in two ways. You can be like, well, this is half the paper, so I must have half. But you can also compute the amount of paper you have in another way. Well, I had 1/3. Plus
Plus, now I can't go.
a 9 plus a 27. Isn't that how my pile was formed? So I think we have this result. Can you please now check it with the, well, is it a geometric series? It is, so let's check it with the geometric sum formula. Does it work? I like seeing geometric series arise naturally, infinite geometric series arise naturally. And I like the algebraic perspective. Let's make sure they agree. Yeah.
If you kept dividing the paper, none of you would have any paper because you'd be splitting atoms and then it would create a massive explosion.
Thank you. Okay.
You just put the atom on my tiny speck of paper so that I can give them another 1/3.
You're doing a great job demonstrating this concept. Thank you,
I
Kim.
did 10 of them because
I'm really happy that someone, at least one person, has chosen to make this a reality. Does it work? Anyone try this formula? Does it work?
Yes.
Alexis says it does. Amar says it does. So let's move on. More practice. Here we go. Let's if they converge, find the sum. These are all geometric. I'll promise that to you. So go ahead and find the sum of all those.
Why did you do that so fast? Oh, never mind.
Plug in one.
When you're ready, feel free to put your answers up here. Those who have been called to the board, go ahead and put your answers up.
How you find that?
What is R, you mean?
Yeah.
R should be obvious from the equation, the form of the equation. What? Sorry, I shouldn't use the word obvious. Obvious is the most dangerous word in mathematics.
It's the common ratio.
Yeah, whatever the common ratio.
Yeah, but when does it
What is the common ratio of the first one?
Well, it's 1/2.
Right.
But then it doesn't.
Wait, what?
It says if like one is greater than 1/2, so like 1/2 is 1/2.
If R is 1/2, which is less than 1, then the sum equals the first term divided by 1 minus your R.
I know why he was wrong.
So you're good. And you should just find the sum. Yeah, whatever work there is to show. Sure. So do the people who are being called before know who they are?
Well, I don't combine the trade from the thing. At a certain point, I create for people.
So, do you agree though that under the definition
This is the explicit one.
what it means for
So this is the first term. This is R.
under
And
that
then it's always like F.
so you
Or the first one is one. This is R.
Well, there are multiple mathematicians that agree on something and disagree on others.
I'm not sure.
I'm saying is if you agree that it's by the arrow box,
That's wrong.
you do agree that
Did it right.
Wait, it's one.
you need to give me a
No, why not the zero is one? That comes
under your
to.
definition. You need to make clear
Yes, you did it right.
You were right. You were right. Wait, you were right. Right. 2 divided by 1/2 is 4. Wait, no, but isn't it A?
No. Yeah, 1 minus your hammer. No.
I know you give
You literally just come into the room and check that. What?
12, oh wait, remember 12 10? over 11 tenths. So,
But I know that in another sense, it can be considered as equal to 1/2, but there are other people who believe that it is divergent enough to count against some. It's a bit of a mess, and I was trying to point out.
Who's CZ? You know who that is? Which that one doesn't do. But certain versus series, there are stages.
Am I supposed to write all the sums?
Okay, go to self.
Is that what you're doing? Yeah, I thought so.
All right, are we betting? Are we betting the answers as they come?
yes.
Here's a bonus problem too. Converge or diverge? Think about it. You might need it.
Unfortunately, 7 pi.
22 over 7 is not 5.
Pi is less than 1.
Right? 22 over 7 is close to 5.
Then you need to fire every single teacher that has ever taught
You
you.
had a teacher that told you that 5 equal 22 over 7? Yeah, show me where that person
No,
is.
I had a teacher that
I'll
looked
give
like a
them a
big
Swift
jelly
pick for
bean.
you. Yeah.
And he said
Why is he rational, which by definition means
his name was
ratio
Mr.
can't be
Oddblocker,
expressed
atomic message,
as a
he
ratio
was
of
the
two
dumbest
integers.
man I've ever teach back.
well, let's go talk to him about it. Let's tell him how. That would be really kind of nice. Let's go tell him how.
You can point out that it's not
I got like
range over 7 is great.
All right, someone had a.
5.
All right, let's. Sorry, this has been so exciting. I realize that. Okay. Someone had a question about the last result. No questions on the first 3 results, though. Is that correct? Okay. You got a question on C? Yeah, this person did not show their work at all. Let's have a seat, Ian. Thank you. Okay. Yeah. So I don't know. I didn't work it out, but it should be. Let's see. It should be. What's the first term? 4 over 1 minus negative 0.3. So that'd be 4 over 1.3. Or 4 over 13 tenths, or 40 over 13, which is what I get. Good. Okay. So I agree with Ruben on that. Annabelle, did you follow my rankings? Okay. And then someone had a question on the last one, or no, they didn't? That's okay. All right. Good. And what is the answer to this bonus question? Yeah, divergence, but just barely. It's 22 over 7 pi is just a hair over 1, so it diverges. All right, stare at this picture until you realize that it's saying something to you.
I see a bunch of
What result? What infinite series result does it say to you?
It's infinite.
1/2 is the sum of 1/2 to the infinite power of 1.
Turn to your neighbor and tell them what result that you see, what mathematical, what algebraic result
It equals 1.
that you see in that picture.
This pattern equals 1.
Sum of 1/2 to the infinite
What'd you say?
power
What did Amara
If
say?
anybody ever told you you couldn't add a fraction to one, you couldn't get an infinite number of fractional
What do you think?
no matter how many added to it, I can't find it.
What
If
do you
they ever
think?
told you
What about
they were using it like a power skill.
what is one label, or what are you saying about one? All right, finish your thought. Okay.
1/2 is the first term, and it is also R.
A question that has arisen up in the front of the room here is, what do the numbers in the picture represent? What, does anyone, what is, thanks,
Yeah.
let's come to order, thanks. Does someone want to volunteer and answer to that? What do the numbers in the picture represent? When we say that this is 1/2 or whatever, what do we mean by one? How is this picture representing 1/2? Like, what do you mean by 1/2? Area is the key word, right? So 1/2 is the area of this triangle, supposing that what is true? I mean, that's only, that the whole thing is 1, right? Okay, so now let's hear from someone about what result that they saw in this picture. Go ahead, Vivian. Give us your result that you discussed. What'd you say? All right, so say it in math, in as an equation. Right. Good. Equals 1. She says. Is that what you saw too?
Yes.
Someone, I don't know. Did anyone else want to say what they saw? Maybe that's what you saw. Someone else said that they saw this in my other class.
Equals 1/2.
Equals 1/2 too, right? Like clearly this sum equals 1/2. In fact, you could use that logic repeatedly about this picture. We'll finish on this slide here. This is kind of the same question we encountered earlier in this discussion today with the 0.3 repeating situation. This is like us revisiting elementary school for a moment, right? But now, as we revisit elementary school, we can tell our uninformed elementary school friends that this really means what? 5 plus 0.172 plus 0.000172 plus 0.00000172 plus etc. Right? And this part is not the 5, but the other part is a what? An infinite, not just any series, but an infinite geometric series, right? So its sum is, what's the first term? 172 1,000ths over 1 minus, the common ratio is also 1 1,000th, right? So we say that as a fraction, that this is what? 5 and, what does this come out to be?
172 over 9.
Well, this will be what? 1 minus 1 over 1,000 is 999 over 1,000.
Oh yeah.
So you'll get what? 172 over 999. So this allows you, though there are other ways to access this result. The infinite geometric sum formula that we've developed today allows you to gain access to a conversion from infinite repeating decimals to fractions. Now, if you'd like to make this instead of mixed improper, you're welcome to. You can do the job of multiplying 5 by 999 and adding 172 and making an improper fraction. All right, good place to stop for today. As we launch into our discussion tomorrow, we'll consider other infinite series as well. Yeah, let's only do homework 3 from the book, the portion of the homework from the book. Okay?